So hello everyone. Hello everyone. So we will be starting a week 9 lecture. With initially we'll start with some intuition of what are the things that is covered in week 9. Then we will go to the finally the questions that is there for week 9 last year. Okay. So basically in week 9 if we see, so firstly the sir initiated the concept of null space, row space, column space, and null space of A transpose. So what we found, the null space and the row space are perpendicular to each other. Okay, so how they are perpendicular, so that we are going to see here, and from there only we will find out some of the properties of uh, some of the properties of uh, positive semi-definite matrices and uh, uh, how to derive the proof of positive semi-definite matrices. So all those things that we will take care in today's class. Okay, so moving ahead. So you all know the null space is defined using this x belongs to r power n for all x such that ax is equals to 0. Okay, that is one of the subspace of R power n. So reminding you again about the subspace. The subspace is nothing but uh, closed under vector addition and scalar multiplications, provided they also a part of the vector space. So in that case, we can tell that is a subspace. So, so subspace will be the subset of that vector space. Okay, any subspace, provided it also follows closed under vector addition and scalar multiplication. I hope this is clear. Okay. So moving ahead, these are the things that we discussed previously. But if you go to the row space, so row space means all of the elements that the part of y is equals to a alpha 1 a1, so on, plus alpha n an. So here the range of all the combination of the all the linear combination of the columns of any matrix, any invertible matrix that is A will be the here row space. Okay, sorry, row space, no, range space. Okay, that is called range space or also called column space. So row space is different and range space is different that you have to take care. This is range space that is equivalent to column space. Okay, what is uh, this is row space. If we call it this R of A transpose means range of A transpose, that will be the row space, because here we are talking about the span of columns of A transpose. Okay, and if you talk about the null space of A transpose, then it is null space of A transpose Y is equals to 0. It is a subspace of R power M. Why R power M? Because here you cannot multiply this if because M cross N is actually uh, the dimension of A, but A transpose will have dimension of N cross M. So Y should always belongs to M cross 1 vector. So basically what I'm trying to tell, you should be able to judge like where it will belong. So if you talk about the range space, so range space and the column space, it belongs to the row R power m, whereas the null space belongs to R power n. So m cross n is actually the dimension of the matrix. Okay. So fine, I hope this is clear, because that null space, range space, column space, and these things are very very important, and these are the important pillars of the vector space in linear algebra. And we should also know that in what cases it is perpendicular to which subspace. So what we have found, that the null space, which is, I'll take a different color. the null space. Suppose this is null space. Okay, so anyone who can tell the null space will be perpendicular to row space. This is row space. This is null space. Okay. Similarly, if you apply the same logic, the column space will be perpendicular to null space of A transpose. Okay. And basically perpendicular we should know that they should belongs to same R power n. See, this is R power n and this is R power n. Otherwise, suppose there are different vectors, then we cannot say, we can't comment on row space and the column space on that. Okay. So moving ahead, so sir taught like how we can derive that it's this is column space, the null space of A is perpendicular to the row space of A transpose. So basically the derivation will comes from if two spaces or if any two vectors are perpendicular, so their inner product will be 0. So let's take any x that is belonging to null space. So it means Ax is equals to 0. Similarly, if you transpose it, it will be 0. Okay. And for row space, what you need? You need A transpose x is equals to y, right? Because transpose you are taking care of, right? Here A y is equals to linear combination of columns of A transpose. Here linear combination of columns of A is there, but if you talk about the range space, so it will be y belongs to R power n such that y is equals to x1 a1 so on xn an, where a1 a2 so on an are columns of A transpose. Okay, so this is the basis of it. Okay, so it means that we have to write y is equals to some h ax, right? Because these are columns of A transpose, so we need to write y equals to A transpose x. We are starting with a very initial, so this y is equals to A transpose x. So if we are writing y is equals to A transpose A, or we are first keeping the x belongs to a null space of A, this means that you need to write x transpose or x transpose A transpose y should be 0. This belongs to a row space, range space of A transpose, that is perpendicular. Okay, so this proves that this is belonging to this. Okay, once we prove that it is belonging to range space of A transpose, then this x transpose A transpose y is equals to 0. This implies x transpose A transpose y is equals to 0. Okay, this means this is already belonging to null space of A and it is also multiplied with y. So this is so this is what it is belongings to null space of A. Okay. Uh, Now moving ahead, I hope this is clear. You should always know. So what I told, null space of any vector, any matrix that is invertible, that has null space, it is perpendicular to row space. Similarly, the column space of any matrix is perpendicular to null space of A transpose. These are the bases for any space, vector spaces in matrices. Okay. Now every non-zero eigenvalue of A, B and BA is same. So sir also proved this, how it is same. Okay. So let's say if we say A belongs to R m cross n, and B belongs to uh, R m cross n. So for any non-zero eigenvalue, you can write this matrix as AB is equal to lambda x. Okay. So B lambda x is equals to B. You can also write this lambda x is equals to ABX. Okay. Similarly, we proved it. AB have same eigenvalue as BA. Okay. So lambda is a eigen value of BA with eigenvector BX. So note, if B belongs to R n cross n invertible, and R is also belongs to n cross n invertible square matrices. So if there exists B inverse ABB is equals to BB transpose AB, then this AB and BA are similar. Okay, so for similar matrices, we also saw previously that A and B are similar if you can write if there exist invertible matrix P, okay, such that B is equals to P inverse AP. Now, if we see both of these two matrices A and B, how they are similar. So basically, this eigenvalue is nothing if you say
lambda n
they are.
eigenvalues that are sitting in lambda diagonal matrix are the
One second,
eigenvalues,
one
right?
second,
So that is what I have. So if this is what I have, and because this is a positive,
one second. Yeah, hello. Yeah. So if you see the eigenvalue uh, of the two matrices, that is A and the B. So basically, if you see this, if you can write B is equals to P inverse AB, so what happens? The both matrices are same but in different bases. Okay, so base is nothing but set of independent vectors where you can define every element in terms of that uniquely determined by in terms of that basis. Okay, so simple basis is I, J, and K. That is a unit vector, but you can have different other bases also. For example, you can have the independent column of the matrix as the unique basis. Okay, that we know. Okay, but if you write IJK, the same matrix in the some other basis, then these two matrices will be the other matrix that is formed using that basis will be B matrix. Okay, so that matrix with the previous matrix is similar. They have similar eigenvalues, means similar with same eigenvalues, just a way of representation. So similar eigenvalues have some properties. What are those? But the first property is same eigenvalue. If they have same eigenvalue, so as we know, the there are matrices where with the same eigenvalue you can have same eigenvector as well. So using that same eigenvector, you can determine that orthogonality and symmetricity or positive semi-definite matrices out of that. So these are some use cases of the similar matrices. Okay, now we are moving towards positive semi-definite matrices. Okay, so if A, this is very very important. In the last class only I told about the positive semi-definite matrices, but here also we are trying to tell again. So if A belongs to M cross N and A transpose A belongs to R power n cross n, and A transpose belongs to R m cross m. So if non-zero eigenvalues are the same as those of A transpose. So see, this is also one of the property that A transpose A have same eigenvalues as A transpose. So m minus n eigenvalues of A transpose are 0. So this will be used in where singular value decomposition. Okay. So A has linearly independent columns and A transpose is symmetric positive definite matrix. All the eigenvalues of A transpose A are strictly positive. So as we know, if you convert the symmetric matrices into PSD, then the eigenvalues of the symmetric matrices will be greater than 0. Okay, so what is the difference between if you see the positive definite matrices and symmetric matrices? So I'm telling you, the positive semi-definite or positive definite matrices are a kind of symmetric matrices which have certain other properties, with in addition to the properties that symmetric matrices shows. Okay, so symmetric matrices, what they showed? They showed that they have real eigenvalue. Okay, and also, for a distinct eigenvalues, there exist independent eigenvectors in case of symmetric matrices. But in case of symmetric matrices, if x transpose ax is greater than equal to 0, then that matrix becomes positive semi-definite matrix, right? In case of say positive semi-definite, in addition to real values, the values of the eigenvalues should be greater than 0. Okay, so that property added in uh, this positive semi-definite matrix. Now you may wonder how these properties helps, okay, and why this properties is important. So if you see, so these properties important in case of finding the real coefficients or in finding the convexity of the function, because in that case the Hessian matrix or the second derivative of the matrix or the function should be strictly greater than equal to 0. Okay, so moving ahead, singular value decomposition. Now this comes to singular value decomposition, one of the most important topic in linear algebra. Okay, so if you see, let's define like this. Okay, so for any, now one question, where it is used. So any rectangular or any kind of different types of matrices, this a singular value decomposition works. So here not necessarily that we need to have a square matrix. Okay, the first thing. So in eigenvalue decomposition, that we decomposed the any square matrix. So in eigenvalue decomposition we saw that matrix should be only square. Okay, the first condition was that, and it should be invertible as well. But here it is not like that. Okay, here any matrices, any sort of matrices is okay, we can do the singular value decomposition. So one of the basic thing that we saw during eigenvalue decomposition, that we can write A is equals to, what we can write, A is equals to A lambda A inverse. Okay, any matrix A we can write like this, where lambda is what, lambda is the eigenvalue, diagonal eigenvalues, and where A inverse is an inverse of the matrix. Now after that we further defined in that case that A inverse will be A transpose in case of symmetric matrices. So on top of it, similarly the positive semi-definite matrices comes. So in that also A transpose is equals to A inverse. Also orthogonal matrices also we will have A transpose equals to A inverse. Okay, so yeah, so here if we have any matrix, I'm trying to relating with the previous one. So if you have A matrix in case of, okay, so if any time at any point of time my voice is not audible, you just text me in the chat box. So in spectral decomposition or eigenvalue eigenvector decomposition, so if you have any matrix B, that is n cross n, necessary to be square, there exists there exists A, which is the eigenvector matrix. That means A is equals to v1 v2 till vn, where v1 v2 vn are v1 v2 vn are eigenvectors, eigenvectors v1 to vn. Also lambda 1 lambda 2 till lambda n eigenvalues. So we could have written B is equals to A lambda A inverse. We wrote like that. Okay, where lambda is nothing but lambda 1 till lambda n 0 0. Okay, so since this decomposition was only defined for square, so we comes to singular value decomposition, where we can also define for rectangular matrices. So since this was very important for the analysis of the matrices, to see the matrices in the spectral form, using the eigenvalue and eigenvector. So we further define it to singular value decomposition. Okay, I hope this is clear. Now, in case of singular value decomposition, here we are having rectangular matrices as well. So what we found, any we can also here if you see, Ax is equals to lambda x was there. Okay. So we can also write any rectangular matrix in terms of different vector. Okay. A v1 is equals to lambda sigma 1 u1. A v2 is equals to sigma 2 u2. Similarly, A vr is equals to sigma r dr ur. So where v1, v2 till vr are the right singular vectors that we will define later with precisely, where u1, u2, un, which are the left singular vectors. Okay, so what is right and what is left, how to see and how to predict, let us know. So why it is right and left? Because here it is defined in terms of uh, because here it will go to left inverse. Okay, so that's why it written this is right, where this is left. Okay, anyway, we will see. So where R is the rank of the matrix, that is A. Okay, so we can also write it like this: A is equals to, this are some v1, v2, vr plus 1, vn, then u1, u2, ur, then ur plus 1, then um. Then we can also write sigma 1, sigma 2, sigma r, where 0, 0 will go. So here you can write like this: av is equals to uz is sigma. So if you write, and if you know this, v is actually orthogonal matrix. So we know V transpose V is equals to V, V transpose equals to I. This means V transpose equals to V inverse. So if you keep like V here as V inverse, so that will give you V transpose. So that's why this expression comes. Okay. So A is equals to U sigma V transpose, actually posit this singular value decomposition, and where A is nothing but U is nothing but A transpose U is eigenvectors of A transpose, and V is eigenvectors of A transpose A. Okay, I hope this is clear, and how this comes, let us see through the derivation. Okay, so hmm, so if you can video phone has ended. 'दिशान 'दिशान मेरा चार्जर फोन का 8% charge.
Hello.
Excuse me, give me a second. Actually, my internet disconnected.
Okay, okay.
Yeah. Why home is calling? Okay, so sorry, in between my internet got. So yeah, we were talking about singular value decomposition. So this U and V is very important matrices, that U and V both are orthogonal in the sense how they are orthogonal, because we are taking only the eigenvectors of this A transpose A and A transpose, where A transpose and A transpose A are itself the property of orthogonal matrix. Now, one more thing that we need to take care, that this is not just orthogonal, these the columns are also orthonormals. Why these are orthonormals? Because we are multiplying with respect to sigma. Okay, so sigma is very important here. So if you don't normalize with respect to this columns, so this will scale up and scale down accordingly. They should. This video is paused due to problems. What is happening? Am I audible?
Yes, ma'am. Yes, you are audible.
Oh, okay. So sorry. Yeah. So in Google this Google meeting is showing that video is paused or something. So I'm pausing my video to listen to the connection. Okay. So what is happening? So we talked about this A and this U. So later we will define how to derive it. Okay. So in the derivation part you can skip and you can try solving yourself. But the problem is whenever you derive anything, so you should start by your concept, like as we talk about like why we are doing singular value decomposition, why it is important, and what conclusion we will take care from getting from doing the singular value decompositions. So these are the things that we need to have. So the problems that is defined for week 9 are designed in such a way that to use to identify the use of this particular singular value decomposition. Okay, so basically what we are trying to do here. So if you see A transpose, okay, this A transpose is nothing but the rank 1 matrix. Why it is rank 1 matrix? Okay, the thing is you are multiplying the every rows or the columns with respect to any different uh, by flipping this row and the column. This is n, this is n cross n, and this is m cross n. Okay, so you are multiplying this one with this one, you are multiplying this one with this one. So actually what you're doing, this is, if you see, this is m cross m. Okay, these are the rank 1 matrix, in the sense that every rows of this particular matrix are the multiple of one another. So only one matrix that is independent. So here you can also see these up to n vectors. These are also rank 1 matrix, rank 1 matrix, rank 1 matrix. So what you're doing, you're adding every rank 1 matrix to an n number of times. So whenever I think in the week 3 or 4, we saw why we are doing LU decomposition, why we are doing QR decomposition. In that also, the main problem was we cannot determine. Okay, so we cannot determine. We were not able to find the inverse of a matrix. So that's why we were converting every matrix to different lower triangular matrix and upper triangular matrix, because upper triangular matrices will have only the multiplication of the diagonal elements as their determinant. So we could do that. Okay, now also here also if you see, so this x transpose y, so why I was telling that why this is rank 1, because these are actually this x2 multiplication of this particular y1 y2 yn, and this is xm multiplication of yn y2 m. So only one uh, rows are there that is independent. That's why the same motto here also, that is rank 1. So okay, so what is the proper definition of single variant decomposition? It is nothing but a given a matrix A that is belong to a R m cross n. There exist U and V, which is orthonormal, along with orthonormal, and also this diagonal element of size A, almost diagonal. There exist. Okay, there exist where we can write A is equals to U sigma V transpose. There A transpose A is equals to U sigma V transpose ka power transpose, and that if you do this transpose and all, then you are getting this A transpose is equals to U sigma sigma transpose U transpose. So what I'm trying to tell, you are getting uh, this as a, so this V, so you can write like this using the spectral decomposition here only. Okay, this is spectral decomposition. So let us say B is equals to A transpose A. So you're writing B is equals to V lambda V transpose, where V is actually eigenvector of B and lambda is eigenvalue of B. So from here, what we can say, the sigma transpose sigma is actually having same eigenvalues as B, where B is A transpose A. Okay, so in that way, sigma will have how much eigenvalue? The sigma will have root over lambda I as diagonal elements, not lambda I, diagonal elements. Okay, so this first equation states this. Okay, if you go to the second equation, so second equation is giving this A transpose A is equals to U sigma sigma transpose U transpose. So this is, if you consider this as sigma, this is capital lambda dash, and if this is B dash is equals to U transpose using spectral decomposition theorem. So what it is showing? It is showing that U has uh, eigenvectors as A transpose. That's why U and V has different. Okay, so I told that if U will have the eigenvectors as U transpose, where we will have the eigenvectors of A transpose A. Okay, as this sigma dash and the sigma, this lambda dash and the lambda, capital lambda, will have the eigenvalues of sigma transpose sigma, as well as sigma transpose sigma sigma transpose. So this is the basis of everything, and why it is giving like this. From here we can derive. Okay, so this is one of the way how we can derive. Okay, so if you have observed, these are actually the same matrices, because even these are actually the diagonal matrices. So if you multiply either with transpose initially or after also, the same only. So nothing much is there. But one more thing, so we only have the singular values or the lambda values till the rank of a matrix. Okay, because if once the rank is zero, once the rank is less than the total dimension of the rank, then we can say it is not in the one of the eigenvalue will definitely be zero. Okay, apologies for my internet connection today. It is little unstable. I don't know how. But yeah, moving ahead, V has the orthonormal eigenvectors of V. A transpose A has its column, and A transpose U has the orthonormal eigenvectors. So orthonormal is very important here. Okay, so these are sigma. Okay, as I told, these are the non-zero common eigenvalues of A transpose A and A transpose. So can anyone tell me uh, what are the dimension of U and V? So you have A transpose A and AE transpose. What will the dimension of U and V? Okay, so if you see this A, okay, so this A has a dimension of M cross N. So you will have dimension of M cross N. Sigma will have N cross N, and we have N cross N. Okay, then only this multiplication holds. So you can see here you can have rectangular matrix as A, but uh, not V. V is also always have the dimension of N cross N. So I'll just check it now. I think should be like this: A transpose A, M cross N, N cross N, A transpose A, M cross N, N cross M. Okay. Okay, we will verify with later, but I feel like this is the only dimension. But how basically this should be multiplied with this, and okay, if we keep this M cross M, if we keep this is this is for sure uh, N cross N. Okay, N cross N. And constant. Okay, I'll tell you in a while this dimension. I think should be written. Okay. So sorry. So I told correctly only. So yeah, uh, this is the dimension. This should we should remember. So today also I'm getting confused. But yeah, how it is like this. This the dimension of U is R M cross M, because anyway this is M cross N, right? So this M, the first should be M cross N, and this is M cross N. Okay, M cross M, and sigma of size A. Okay, sigma will have size A. Okay, okay. So how this is M, this is M cross N, this is M cross M, this is M cross M, and this is M cross N. Okay, so here we can see this U and V are actually the square matrices. So why we are doing, one of the main reason is also like this, that we are converting the rectangular matrix in terms of a in terms of a square matrix, where we can find the inverse of a matrix, we can find the adjoint of a matrix. Otherwise, the triangular matrices, this rectangular matrices doesn't have the properties to find to have the inverse, to have the solutions. In fact, in case of the tall meters, we saw that there can be possibility that there can be a solution existing or no solution. Okay, so in case of height matrices, we are having so many solutions, infinitely many solutions. So the single solution is not there, or anyway, we just want an efficient and a single solution for every case. Okay, so in that case, this is the way to do the same. Okay, so U has orthonormal eigenvectors of U A transpose, that is columns, and this V has the orthonormal eigenvectors of A transpose A. I hope this is clear. So how to calculate it further? Okay, so if you are given a matrix A, so you can calculate by just calculating firstly U, then V, because anyway we are doing this A Vi is equals to sigma I Ui. Okay, so Vi you can have sigma I Ui divided by, okay, so you can have Ui is equals to A Vi divided by sigma I. Anyway, you can calculate either ui first or ai first. But if you calculate ui first, so if you calculate vi first, then ui can be easily written in terms of this one. Okay. Anyway, these are just this scalars. Okay. So how will we calculate this vi? So vi is nothing but the orthonormal eigenvectors of A transpose A. Okay. So for that you can calculate VIs. Once you have VIs, you can directly calculate UI. So why we are not calculating UI first? Because as we see, U has the dimension of m cross m, and V has a dimension of n cross n, and sigma has a dimension of same m cross n. So this V is just A transpose A. Okay. And this have A transpose. Anyway, you can calculate either the first, but this A transpose A calculation of this one will be easy than this A transpose A transpose. Okay. So we will check with some of the examples also. So if UIs are the eigenvectors of A transpose also, we can calculate this like this A transpose. But yeah, and in both the cases, you don't need to calculate the eigenvector for both the matrices A transpose and A transpose A. The best way to do first calculate for one matrix, that is V, then calculate for the other matrix. Because anyway, if you do the for the same, it will take the same. It will say take double time. Okay. Also, we need to make sure that the columns of the U matrix and the V matrix should be orthonormal. So we need to divide it by the root over the whole magnitude of the vector. Okay. So also we told that the sigma values will be only containing the non-zero values till what one? It will continue non-zero values till the rank of a matrix, that is R. Because anyway, if it doesn't consist, then it will have the zero eigenvalues, and all the diagonal elements will consist of the zero values. Okay, so my screen is not moving. Just give me a second. So actually, my screen is lagging. Today there is lot of problem in the network connection. Same internet only. IITM. Hello, my screen is visible or not?
It's
Okay,
visible.
okay, in my laptop it was not showing. Okay, that's fine. So I'm moving ahead. If you see some of the examples, so let us compute this SBD for this matrix. Okay, so why I'm very much focused on SBD, because SBD is one of the main important thing in linear algebra as well as AIML applications. So yeah, so if we calculate A transpose in A transpose, it will having this one. So if we calculate eigenvectors of A transpose A, so just a guess that we can have since we have the eigenvalues as 45 and the lambda 2 is 5, that is sigma 1 square sigma 2 square. So how can we get the same eigenvalues are like this? So we guess this v1 should be 1 1 and v2 should be minus 1 and 1. How will you guess? So yeah, so doing what operations, it will give you 45. So summing by 1 1 only, it is giving 45. So like this. Okay, this is lambda, this is also lambda. So in a similar way, if you do for the lambda 2, it is giving minus 1 and 1, the same vectors. So yeah, so one of the eigenvector for v1 is 1 1, and v2 is minus 1 and 1. Okay, if you normalize it to have the orthonormal property, so we have to divide it by magnitude of the v1. Okay, so this is 1 by root 2 v1. Okay, so similarly u1 you can calculate for the left singular vectors. So yes, so sometimes I also used to have doubt, like if you are writing a is equals to u sigma v transpose, so which one is will be left and right? Okay, so this u is, since it is written left, so it will be left singular vector, singular in terms of this left of this, and this is the right singular vector, singular vectors. Since the matrix consists of left singular vectors and matrix consists of right singular vectors. So we can calculate this sigma when u1 is equals to a v1. So yeah, using this we can calculate, and we can write sigma 1 u1 v1 transpose, because because we were writing this a v1 is equals to sigma 1 u1. Okay, so if you write like u1 here and sigma 1 here, so v1 inverse, okay, this is u1 sigma 1 v transpose. So this v transpose will go here, so you can write like this. Okay, so since this is all the elements, so it will be the sum of all the elements, so it is giving this. And if you write properly, uh, in this u sigma v transpose, so we have to make sure that sigma 1 should be greater than sigma 2 should be greater than sigma n. Okay, where A is the rank of the matrix. So you can write like this. How can you write? This is what? 1133 root 45 divided by root 20 0 root 5 divided by root 20 0, and this is 3 minus 1 1. Okay, this is U, this is V, and yeah, so root 20 is here. Okay, so this is sigma. Okay, so if you have positive, the symmetric positive definite matrix, so this, so yeah, one more thing. So if you define the same singular value decomposition for symmetric positive definite matrix, so what we have observed, that singular value decomposition is same as eigenvalue decomposition or eigenvector decomposition or spectral decomposition for symmetric positive definite matrix. So for symmetric positive definite matrix, your singular value decomposition is same as the eigenvalue decomposition, where this q is actually u and q transpose is also v, and where q and v is equals to v, and the sigma is actually this capital sigma. Okay, so that is great to know. Okay, so if S belongs to R n cross n is symmetric, but one eigenvalue is negative, so how it is different? Okay, so in that case the difference will be in the sign of singular vector, either left or right, corresponding to negative eigenvalue. So here we restricted our matrix as symmetric positive definite matrix. So in that case we know that sigma, this lambda will be always greater than 0, but if you say for a symmetric positive definite matrix, so in that case it is not greater than 0. Okay, so moving ahead, uh, yeah. So if we have Q is an orthogonal matrix, then A transpose A is equals to I. The all signal values are 1. So one more thing, as we know, for orthonormal or orthogonal matrix, the eigenvalues will be always either +1 or -1. So if we consider only positive values, then U and V. So this is also very important. In case of orthogonal matrix, the U is, and what is V is. Okay, so AQ or AI, you just take care as a homework. We'll go to the questions in the next half. Okay, I'm just trying to cover all the things. If A belongs to R, n cross n be any matrix, the eigenvalues of A should be less than or equals to sigma 1, the maximum singular values. So also, this is also very important. The eigenvalues of any matrix should be less than or equals to maximum singular values. So maximum singular values, what is saying? So if you recall the definition of eigenvalue and eigenvector, so we saw if you draw this plot and if you have any function, so the axis of the rotation is what it is, the eigenvector. So eigenvector defines that the axis where the value of a function is not changing, means you can consider the rotation vector. Okay, and if you multiply any scalar with it, so the magnitude through which it is scaling, okay, but not changing the direction. Okay, since the rotation also doesn't change the direction, so the vector doesn't change the direction in any particular function is called as eigenvector, and the value through which it gets scaled is called eigenvalue. Okay, so uh, so the magnitude of the magnitude of this of the eigenvalues of any matrix should be less than some maximum eigenvalue, or definitely that is given by the sigma 1, because all other eigenvalues should be less than equals to sigma 1. And if you determine this ax mod of ax, okay, so it should be less than if you do the singular value decomposition, and should be less than sigma 1 also. Okay, so what here we are trying to sell this x, the eigenvector corresponding to the eigenvalue lambda. Okay, so here this x is the eigenvalue corresponding to the eigenvector lambda, where lambda should be less than or equals to sigma 1. Okay, so this is, I hope this is clear. If even if it is not clear, you can ask me again. But this is important in the sense that here what you're trying to do, you are, and we saw that this is what maximum magnification. Okay, do you remember what was that? The term was there. Uh, where we sensitivity analysis, yeah. So yeah, in that sensitivity analysis what we saw, the sensitivity analysis what we saw, the magnitude of ax divided by mod of x should be less than or equals to 1, right? So this, and also this kappa function was there, where we can write this as a maximum magnitude of a divided by minimum magnitude of a. I hope you remember, we saw this in the week 5. So, in that way only, we saw that this should be less than or equals to 1 in that case. But for any singular values, if we define, then in that case, it should be less than or equals to sigma 1. Okay. So, this maximum magnitude was defined as max of mod of A x transpose divided by mod of x divided by min of mod of ax divided by x. Because why it is maximum magnitude of x transpose x, because here if you have any function a, so we know that any linear function can be transformed in the terms of a matrix. So if a is transformed in terms of matrix of this circle, and if you magnify with respect to x and divide also by respect to x, so what we saw, this is equals to maximum magnitude in x. Okay, that can be related to eigenvalue of A, that is maximum eigenvalue. So that's why this mod of lambda should be less than or equals to sigma 1. Okay, let's take another example, this x y transpose. So if x is not equal to 0, y not equal to 0, and uh, if you write uh, x as a belongs to r power n, y belongs to r power n, so x y transpose equals to a m cross n, and x by x transpose, you can, how you can write in terms of singular value decomposition. So in terms of singular value decomposition, you can write like this: u1 is equals to x divided by mod of x, and v1 transpose is equals to y transpose divided by mod of y 2. Okay, so sigma 1 is here, mod of x2 and y2. So in the upcoming classes, I'm sure that sir will talk about sensitivity analysis, because we are moving towards it only. The sensitivity analysis using singular value decomposition, that will be the topic. So my screen is lagging, I don't know, but it's fine. But for this particular matrix, because x by transpose is giving you a matrix. Okay, so in particular, for this particular matrix, you can have this type of singular value decomposition, where x u1 is nothing but x mod of x B1 transpose or Y transpose, that is very great, you know. You are just multiplying with x divided mod of x, that is a unit vector. Okay. And B1 transpose is nothing but Y transpose mod of Y, and sigma 1 is nothing but this one. Okay. Magnitude of x and y. So that is, so you are just writing in terms of x y transpose, whereas this will cut, but the remaining term is x y transpose. So yeah, if you see in terms of a circle, so if you write this x is ax and x is equals to u sigma v transpose x, and if a is invertible, rank is 2, and we will have two singular values, and you can write this v as v transpose, then and by doing the similar way as v opposite to v, you can have sigma, and then that is giving you ellipse. Okay, so in that ellipse only we saw about sensitivity analysis, but we will take care in upcoming classes. So this is what. So these are some another way of proving the singular value decomposition. So I think sir thought you take the example using the sensitivity analysis. So maximum of a x square divided mod of x square, you can write like this. Okay, I'm not going into the proof. So yeah, I told this is a minimum magnitude and maximum magnitude is one of the case that we saw in during the sensitivity analysis. But we can also relate with respect to the singular value of any matrices. Okay, so yes, so these are some such proofs. Okay, also a Rayleigh coefficient is quotient. Okay, so this x transpose a divided by x transpose x is actually the Rayleigh quotient. Okay, x transpose a transpose x divided by x transpose x. Okay. I hope this is clear up to this point. Even if it is not clear, you just let me know. Um, and since today, I don't know, due to Holi, there are not many students join. And okay, that's fine. But even if they see the recording, they should have some problem. If they have any problem, you can comment down in my YouTube channel. I will definitely go through the problems. But yeah, this Rayleigh coefficient, you should remember that's X transpose a transpose A X transpose divided by X transpose X. And the proof of the singular value decomposition, we can go through maximum magnitude and minimum magnitude. Okay, so I'm going towards it. So as we know, Frobenius law. So if we write the matrix in terms of vectors, okay, and squaring it and summing out, okay, so that will give you the Frobenius law. So the A2 is actually max of AX divided by X2, as we know this is the 2 norm that we can write like this. So 2 norm you also know, this is A transpose A, magnitude of A transpose A. Okay, divided. This is A transpose A. This will, okay, as we saw in the previous class. But we can also write this max magnitude of A. This is max of x not equal to 0 divided by mod of x. And this is max of x 2, 2 norm is equals to 1. And ax is equal to sigma 1. So this is the maximum singular value of A. So yeah, so as we know, this is a maximum singular value of A. This Frobenius norm is root over summation of I, summation of j, summation of all the elements of any matrix. That will be also can be write like this trace of A transpose A. Okay, and we can also write this Frobenius norm as a root over trace of A transpose A. So this is nothing but, so see how far we have come across. So this Frobenius norm is nothing but the sum of root over all the sigma values. Okay, so that's great that we saw here. So this Eckhart Young theorem, what it states, that if the rank of B is less than equals to k, then mod of a minus b, that is a 2 norm, should be greater than equals to sigma k plus 1. So there are some proofs. Why my screen is not closing? Yeah. So there are some proofs for it. So this theorem is the basis for the above proof that we saw. This is the Frobenius norm. So remember, the Frobenius norm is the root over trace of A transpose A, and if we write the singular value decomposition, so we saw that it is sum of the all the elements of sum of the all the eigen singular values of a particular matrix. So here we are using like this, like we have done the singular value decomposition and we are using the singular value decomposition here. So that is great to know. Okay, so these are some proofs. And lastly, some low rank approximation is there. I think that is not asked in uh, uh, that is not asked in the questions, as I just saw in the question before coming to the class. So we can skip this. We can directly move to the question. But the lower rank approximation is nothing but like how can you uh, approximate a very high rank matrix in terms of low rank matrix? Because anyway, the formulation or the interpretation or the adaptation of the low rank matrices is far easy than the high rank matrices, because if you go higher and higher as n cross n, suppose n is 100, so in case of all independent columns and element rows are there, so doing mathematically and proving everything is very tough there. So that's why we often don't do that. Okay, so yeah, that was the low rank approximation, and there are some formulas that we can directly write like this. Or also, one more important thing is the smallest error of any two rank matrices are there is that is given by the Frobenius norm that we also call as H, that is error. I lost connection. Okay, I'm losing my connection like anything this time. Okay, so this is Frobenius norm. And this low rank approximation I'll tell you in the next class. So I'm moving to the questions that is important for week 9. Then we will end this class. Okay. So okay. Let us give some 5 minutes to understand this question. Meanwhile, I can have water. Yeah. My updated question is visible to you. Like Ananta, can you tell me?
Yes, ma'am.
Yeah, okay, okay. That's great. Okay, so the first question states that state which of the following statements are correct. The first one is the singular values of a square symmetric matrices are the same as its eigenvalues. Okay, square symmetric matrices. Every real matrix has SVD. Okay, the singular values of orthogonal matrices are all one. So, anyone? Any guesses? So, I think square symmetric matrices.
Second and third is
Second, third is correct, you're telling?
yes, by definition.
Hmm, that is for sure. But in case of first also, the singular values only we are taking care. Okay, we are not talking. If it is positive also semi-definite matrix, then the same uh, PSD is actually this, what is singular value decomposition is same as eigenvalue decomposition in case of PSD symmetric matrices. That is also called symmetric. Uh, what is this matrices name is there? Symmetric positive definite matrix. Yeah, this is SPD. For SPD, this is same. But in case of square symmetric matrix, this is also same. Okay. Why? Because this A transpose equals to A in this case, and sigma will have same values as sigma. Okay. So first, second, third, all these things are same. So if we see even fact, some of the solutions. So option 1 and 2 are true by definition. Then,
I have
yeah. Please ask. Yeah, Ananta. Yeah, Ananta,
I
sure.
have doubt in
So sorry, your voice is breaking.
statement one.
Okay, so statement one. Okay, the singular values of a square symmetric matrices are same as its eigenvalue. Why it is same?
In which condition every eigenvalue of a matrix is similar to singular value?
In which condition it is same? Okay, so see, similar matrices are different here. Okay, similar matrices, what we told, if they are A and B are similar. Okay, if there exist A is equals to there, if there exists uh an invertible. My connection is lost in like
No, my question is,
huh. Yeah.
hello,
Hmm. Please tell me.
in which case
In which case,
for a matrix
for a matrix,
every singular value,
every.
every eigenvalues and singular values are equal.
Okay, so as I told, in case of symmetric positive definite matrices, the singular value decomposition is actually it is exactly same as eigenvalue decomposition. Exactly same. Okay. In that case, this if you have A matrix, then you can write A as V, this V transpose. Then this V is actually A transpose A eigenvalues, and this similar to U, and this V is also V. So U is V in this case of this SPD, symmetric positive definite matrix. But if you're talking only about the this matrix, not about U and V, okay, then in that case symmetricity is required, because anyway we saw in that. Somewhere I saw told you. Yeah, so if it is symmetric positive definite, so this is the case. I'm so sorry, today I think some internet issues there in my hostel, so that's why many times it is going and coming. So yeah, in case of symmetric positive definite matrices, this is same. But if you talk only about this, okay, so for that symmetricity is required. Okay, so this is one of the property uh, that is there. Okay, so if you go to the, yeah, so can you can Ananda tell me the what will the rank of A in this case? This is very simple, straightforward.
In which, ma'am? First one?
Second question. First question, did you get it?
Yes, yes. Here it is 3.
Okay, very nice. So it is 3 only because we saw the sigma will have the values only sigma 1, 2, sigma r, else not 0. So that's why. Okay, let's solve this question.
Ma'am,
Yeah, yeah.
in question number second, if suppose there is 0 is one of the eigenvalue, is that condition is possible? Like 502.
Yeah, yeah. Here, this see, this is in fact, since this A is having 5 plus 5, and you're having this only rank 3, so definitely this it will have 0 as one of the eigenvalues. But it doesn't restrict you to write in the not in the terms of this singular decomposition. In the either way, you can write in terms of singular decomposition. So this is valid for all. You can write. But the only thing
Okay.
is this value should be in the decreasing order according to the
Yes,
formulations.
yes, singular value.
Yeah, yeah. Can you repeat?
Yes, we can write in decreasing order.
Yeah, yeah, yeah.
Maximum first and minimum then
Yeah, yeah.
afterwards.
Anyway, zero is one of the eigenvalue of this matrix. That's why this zero
Suppose
is
502 are the eigenvalues and other two entries are 0. Then that rank is
rank will
2.
be 2.
Yes.
502, then 520 you have to write.
Hmm.
Yeah, yeah. Okay. So you have to tell how many statements are correct in this case. So pseudo inverse, this is what left inverse. Pseudo inverse actually A transpose A, whole inverse A transpose into, yeah, this is pseudo inverse. And in case of the tall matrix, you can't write if in case of tall matrix where you have more number of equations and less number of unknowns, so you can also have the possibility that no solution, and it can have the possibility of one solution. Okay, one unique solution or no solution. So in case of no solution, what we try to do, we try to approximate it. Okay, so that we will have the less error. So that's why we got this A inverse. So X is actually this A inverse Y in case of tall matrix. This is tall. Okay, this is pseudo-inverse. Okay, so if R of A denote the rank of a matrix, state which of the following statements are correct. Oh, that's great. SVD can be used to calculate rank of a matrix. It is correct. Okay, this is also correct. Why this is correct? Because this rank of A. Uh, basically, this tall matrix have the property that it will have linearly independent columns. Okay, so anyway, that linearly independent columns of A, uh, pseudo inverse of A, that will be A transpose A whole inverse A transpose. So this is giving you again the A transpose A, that is full rank, and this is also giving you full rank. Okay, so yeah, this A transpose A will give you full rank, and this A transpose will be divided. So anyway, the rank of A transpose and A is equal. So from that case, this is correct. And if you see this sigma I, So yes, this will also be correct. I think the answer is C. 1 and 3. Second is not correct. So yeah, second is not correct. Let's see why it's not correct. But I hope this is clear. The rank of A is Y rank of A plus, because this is full rank. Okay. So this anyway it won't affect. But this A transpose, the rank of A transpose and A is same. So that's why this is same. And as we know, this SVT can be used to calculate rank of matrix from the calculating non-zero singular values. So this is correct. And why this is not correct? Because sigma I is an inverse of sigma and okay. Oh, okay. So sorry. So this U and V will change definitely for A positive. Okay. Because A positive is not equals to A. So this the calculation that is done for A, that will be U, it will not be equals to same for A positive. So that's why the second will not correct, and answer is C. Answer is
How?
C, but they are telling all A first and second and third are true and they come from definition. What should be the answer? I'm not sure of the answer. But if they're telling the C, I think the answer is D only. That's why this D is there. So first question is correct, I hope. So let us solve for A plus. Okay. So for U is actually A transpose. Okay. So if you replace by this A plus transpose, so means eigenvectors only. So if the matrix is same, then it will be same. Okay. So A plus is what? A transpose A inverse. A transpose. This is A transpose A inverse. A transpose transpose. Okay. That's why for the first view only I was telling that it should be correct. But let's see. This is A inverse A transpose inverse. This is A transpose. This is A. This is A transpose A whole transpose inverse. Okay. This is I. This is A inverse. This is A. This is A inverse transpose A inverse. This is this is this is also giving you I. This is A transpose just into what I did. B transpose here it will be coming. This is A transpose inverse and transpose power transpose. It will be negative. So here it should be like this. Okay. So what I got is A transpose inverse A inverse, which I can write like A transpose whole inverse. Okay. So what I got U for A positive is this one. Okay. Similarly, this V for A positive will be uh, V for A positive will be A transpose A whole inverse. Okay. Now we know uh, this U and V since orthonormal. Okay. This U and V are orthonormal. So U inverse is equals to U. No, it will not be the case. U for A positive. So let's write this positive positive. Okay, yeah. So as we know, if you have A inverse, sorry, if you have A as has eigenvalue of lambda, so A inverse has eigenvalue of 1 by lambda. Okay. So rest the eigenvectors are same eigenvectors. Okay. Similarly, if we have uh, A has singular value decomposition as sigma, so A positive will have singular value decomposition as sigma inverse, rest eigenvectors as same. So that's why both will have same. In fact, you're getting negative. In fact, this one also, but the eigenvectors will be same only. because inverse, how the inverse we are calculating? Adjoint of A divided by mod of A. So mod of A will not only won't affect the eigenvectors, but adjoint you are calculating the minus, so it won't affect. So you can take this two properties and you can derive this too. This A positive will have only effect of this as chain, otherwise all same. Because this A positive is actually the inverse only. Okay. So here from this we can say, if even if you have doubt, I'll prove these two concepts next class. But yeah, these two concepts you can take as a reference and we can prove that this is same. So I think the answer will be all first, second, third. Just written wrong here, so it should be D. The singular values of a matrix are, what are the singular values of a matrix? If you can write, what should be the answer here?
C.
Okay. But how you're writing as a C?
Sigma square is equals to lambda.
Okay. But you can write like A as, since this
2r.
is, no, you can write A as I transport, right? 220. The answer is A only, right? Because you can write this I transpose. This I is U. This is V transpose. You don't need to do this under root. So that's why the answer is A. This is symmetric matrices and also positive definite. The same, the singular eigenvalue decomposition will also be same here. That will be V, the V transpose. Same as U, sigma V transpose. So this will be sigma values, right? Sigma 1, sigma 2, 0, 0. So answer is C,
Hmm.
A. Okay. So let's see this answer. If RA denote,
Ma'am,
yeah, yeah,
if the matrix is symmetric and positive semi-definite,
yeah, symmetric,
what
positive,
happens in that?
definite. Yeah, yeah. Can you repeat?
Symmetric but positive semi-definite.
In that case, it can be equal to 0. It is not
Hmm.
required strictly
Yes.
greater than 0. Semi-definite means equal to sign will come. Because if it is
Hmm. Hmm.
associated with x transpose x, it equals to this 0 for positive semi-definite. If it is definite, then greater than 0. But here we are talking about positive definite. Okay. Not positive
Hmm.
semi-definite.
Means if the matrix is positive semi-definite
Then this will
symmetry,
not hold.
this not hold.
Nah.
Means we need to calculate and then we need it is sigma square equals to lambda.
Yeah.
In that case, the option is C is true.
Uh,
Suppose A is equals to 2000.
that's fine. That's fine. But anyway, you are able to write in this, try to write like this. I have multiplied with I. Okay. This I.
Hmm.
But even if it is 0 here, this this matrix is not changing, right? So if you relate this I as U and this I transpose as V transpose, sigma is same,
Hmm.
right? In that case also
Hmm.
sigma 1 is equals to 2, sigma 2 will be 0.
Hmm.
It won't be root 2 in that case as well.
Okay.
Yeah. So let us solve this question, question number 5th. If RA denotes the rank of a matrix and RW denotes the rank of a matrix as UV, then the rank of UV, I think the rank of W is a well derived formula, is actually the minimum of rank of U and V. This is the formula. So the minimum means answer D only. This is a well derived formula that follows from the definition. Why it is like this? Because this uv is actually the multiplication of u and v, and if you do this, it is actually one row and one column, then one row and one column, then one row and one column. So if you try to get the same values, so it's actually the inner product of this row and this column, and this row and this column. So if it is not minimum, you can't derive this. So this rank is actually minimum of this way in case of the multiplication. So this follows on the definition. So Frobenius norm. What will the Frobenius norm? That will be very same. 1 plus 1 root 2. This is root 2. Answer is C. Okay, this is not Frobenius.
No.
Yeah, this is
Yeah.
2 norm. So this is A transpose A. Root over A transpose A, right? This is 1001. This is
B option.
01. Sorry. This is 10.
Same.
A transpose is actually what?
Identity matrix, no?
Huh? Okay, this is identity matrix. Okay. This is 1 minus 0. Fine. Hmm. Answer B. So what I was trying to do, Frobenius norm. Okay, this is actually the sum of a1 square plus a2 square, so on, plus an square. This is 1 plus 1, this is root 2. In case of Frobenius norm, it will be this one. This is the maximum magnification produced by the identity matrix is 1. Okay, this is the Frobenius norm. You can calculate it with.
Ma'am, since it is identity matrix, it is trivial. But if you take any other matrix
Huh.
with non-zero entries, then how?
The other matrix has the non-zero. This is this one.
Okay.
Using this formula, we can calculate. Or this is also equals to max of ax divided by mod of x. This same. Frobenius norm, I think we can directly calculate, say, sum of all the squares of the elements of the matrix. So, yeah, this is very simple, straightforward. What should be the answer for 8? If A denotes the R n cross n denote the covariance matrix, okay, then the eigenvector corresponding to mod of A2 corresponds to the direction of,
Maximum variance.
yeah, maximum covariance is there, so maximum variance. Okay, this is eigenvector corresponds to maximum recognition is through maximum variance. Yeah, very nice. Find the nullity of the matrix. So the nullity is rank minus, nullity is what?
Dimension minus rank.
Dimension minus rank. Yeah. So we need to calculate the rank. This is actually the
1,
rank is 1.
1, and 3 minus 2.
3 minus 2, 1. Okay. Let's see the answer. Nice. Hmm?
Ma'am, I have doubt on the question you have written.
Which question?
6.
Hmm.
Norm of 2 norm is equals to
Yeah, this,
root of A transpose A.
yes. For a matrix, we define like this. A transpose A, root over A transpose A.
For any square matrix, it is equals to.
Yeah, I think in some of the week, sir only gave this formula. I think week 7 or something like that. I'll just
Because we are taking square root of square matrix.
uh the this I'm sure about this particular formula, the second formula that I told, this one.
Hmm.
Okay, this is
Hmm.
sure, and associated with this
And
is
first one,
something.
huh?
Wait, we can calculate using with this we can calculate, but let us see for this. I will also have some doubt. Week 7, week 7 only he taught, I think. Mhm, mhm, mhm. See, this for any p norm we can calculate its max of ax. For 2 norm was equal to, okay, yeah. So we cannot directly write like root over A transpose A. But yeah, the eigenvalue of A transpose A, the largest eigenvalue of A transpose A will be the 2 norm. So somewhere I wrote, so I forgot that largest eigenvalue. The So I think weeks 4 or 5. So your doubt is very nice that how can we just get a value out of doing the square root of A transpose A? Okay, going back to it,
Hmm.
this is this is not simply this one. This is maximum of this one only. So this 2 norm of any matrix is given by maximum
I think there is might be a summation. I think
summation. No, but you can relate like this: maximum eigenvalue of root over A transpose A. But A transpose A somewhere was there.
hmm
I don't remember much, but we can just think like how it is. But yeah, we are only left with one last question. So this question is, if it is SVD of A, then which of the following statement is true or not? So can we write like this? Frobenius norm. So if we write A is equals to U sigma V transpose, the sigma is actually a diagonal element with ordered singular values. In such scenario, if we replace sigma I with sigma 1, we get A less than equals to this one. This implies if A is less than, then all the elements sum is also less than this one. How it is less than? Because this is only one sigma 1. Okay, so it should be less than with respect to all sigma 1 also. So if you write like this, so the statement is true. And this is a well-defined proof that we can refer. This is true that Frobenius norm of a matrix is less than equals to the 2 norm multiplied by U V transpose Frobenius norm. So yeah, so we will end the class now. Like we covered some of the class questions. There are not many students join this class. Yeah. Any doubt? You just
no, ma'am.
yeah. Okay. So thank you for joining. We can end the class now.
Thank you.
Yeah. Thank you. Okay. So sorry, I think I was not audible. So I'll end the class due to some network issues. So thank you so much for joining. Okay.